Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 29th video lecture. And we're going to begin today with a kind of a very interesting statement and a very technical proof. And then we're going to move on to kind of a slightly different topic, even though it's going to involve uniform convergence. But it's going to involve some boundedness properties as well. So here's what we have in terms of the start. Theorem. There exists a real continuous function on the real line which is nowhere differentiable. In my opinion, this is a little bit remarkable. Here's the proof. So we're going to create this function. We define phi of x being equal to the absolute value of x. Well, that's not so special, but we're just going to look at it on -1 to 1. And then expand the definition such that so that phi of x plus 2 equals to phi of x. And this is for all x element of R. So we now define this function on the whole real line. What does this function look like? Let's take a look at its graph. Okay, so its graph looks like this. Okay, so 1, -1, that's 0, we have 1 here. This is what it looks like. And now this repeats. And so we just move this every 2 units. So there's 2, 3, we'll get the same V looking shape. Okay, and then of course we can extend it a little further. 4, 5. And then it's going to continue in this pattern. And then we back it up, -2, -3. And it keeps on doing this pattern. Okay. So that's what it looks like. Now, since the absolute value of S minus absolute value of t, something we used not that long ago, is less than the absolute value of S minus t, then, for all S and T in R, we have, okay, just using this with our notation for phi, this is phi of S minus phi of T is less than or equal to S minus T. Okay, now, if you let x be an element of R, then, and epsilon be greater than 0 be given. Then for all, I'm working on continuity here. for all t element of R with t minus x inside absolute value being less than epsilon, then phi of t minus phi of x inside absolute values will be less than epsilon because of this property. So that says phi of t, if you will, or phi, I'll just write it that way, is continuous. It's continuous at this x, but that was just an arbitrary x, so it's continuous on the whole real number line. This obviously isn't a function that's nowhere differentiable. I mean, it's not differentiable at these sharp corners, but we've got to do something a little bit more creative to get the function we need. Okay, now we define f of x to be equal to the sum as n goes from 0 to infinity of 3/4 to the n phi of 4 to the n x. Okay. And I'm just going to make this, well, I'll say which exists. What I mean by exists is that this summation converges for each x in R, okay, as the sum as n runs from 0 to infinity, 3/4 to the n times phi of 4 to the n times x converges, saying. And I'm going to take some time to explain why this converges. Because this phi of 4 to the n times x is definitely sandwiched in between 1 and 0, you can see from the graph that we had drawn. So this sum that we're looking at, this series, is definitely going to be less than or equal to this sum, where I'm just replacing that part with 1. And that is a geometric series Thus, this sum as n runs from 0 to infinity, 3/4 to the n times phi of 4 to the n x converges by the comparison test. Excellent. Now, since the absolute value of 3/4 to the n, phi of 4 to the n x is less than or equal to 3/4 to the n, which is equal to 3/4 to the n, so that's the value of a positive number is itself. And the sum, as n runs from 0 to infinity, of 3/4 to the n converges, because it's a geometric series. Then by a previous theorem, the sequence of functions, let's say n running from 0 to k, of 3/4 to the n, phi of 4 to the n x, converge, this is as k runs from 0 to infinity, converge uniformly to f of x, which we define to be that limit function. And then since f of k of x equals to the sum as n runs from 0 to k of 3/4 to the n, phi of 4n, 4 raised to n times x. Since that's what we have, is continuous. Okay, so that's a continuous function. And it's continuous because it's a sum of continuous functions. This is a composition of continuous functions. 4n is a constant times x. That's continuous. Phi acting on it's going to be continuous because phi is continuous. And then we're just multiplying it by a constant. And we're adding a bunch of those up. And the addition of continuous functions is continuous. Okay. And the fact that, then by a previous theorem, I should say, because we have convergence uniformly. Then by a previous theorem, okay, we have f of x is continuous on R. Okay, now, here's what we're going to fix x down on bar. So we've got this guy fixed. And m and a positive integer m. Okay, now we're going to put delta sub m equal to 1/2 times 4 raised to the minus m power. And it's going to be plus or minus this. Where the plus or minus is determined by by the fact or by having no integer line, no integer lies between 4m times x and 4m times x plus delta sub m, which I'll say that that is the same thing as 4m x plus, this will be plus or minus 1/2. The idea here is this 4 raised to m times x. That quantity is a number. So it's here on the number line, here it says. Okay. Now, it might be an integer, I don't know. But let's say it's got an integer somewhere close to it. Then the next integer bigger than it, if it's close to this left-hand integer, then there's a pretty decent gap here. And so we'll take the plus version of delta sub n. If it happened to be the case that the 4mx was over here close to this integer, we take the minus 1. But regardless, anytime we get we're going to be able to get a region about 4mx if we go half a unit from one direction, one or the other, that it won't contain an integer. That's going to be important from the graph later, some aspect that we'll be working with. Now, we're going to define, oops. We're going to define this number, gamma of n, and it's going to be equal to phi of 4n times x plus delta sub n minus phi of 4 to the n times x all over delta sub n. What a crazy looking quantity. Now, we're going to talk about this gamma sub n. When n is bigger than this fixed m, okay, then what we have is 4 to the n delta sub m equals to 4 to the n times, it's either plus or minus, 1/2 4 to the minus m. Now look, we're saying n is bigger than m, and so the n, if we take the 4 to the minus n, that's 1 over 4 to the m. The n is bigger, and so this is at least going to be 4 when we multiply by plus or minus 1/2. What we're going to get is something that is going to be an even integer. And in this case, this gamma of n, which equals to phi of 4n x plus, this guy is, well, let me write it down. Here it is in front of us. So it's 4n x plus 4n delta sub m minus phi of 4n times x over delta sub m. But because of the way that phi was defined, remember it had that property that phi of x plus 2 was equal to phi of x. So here we're taking phi of something and we're adding an even number to it, if you will. And that's going to make it the same as just phi of this. So here, I'll write that out. Over delta sub m, and of course that's 0. Aha. Okay. Well, when 0 is less than or equal to n is less than or equal to m, the norm, or the absolute value of gamma sub n, is equal to, well, it's the norm of the phi acting on 4n times x minus x plus delta sub m minus phi acting on 4n times x all over the delta sub m, okay, which is going to be less than or equal to so this is 4n times x plus delta sub m minus 4nx. Remember, the phi is defined to be the absolute value of these guys. All over the delta sub m. So I'm using that factor I've used before. The absolute value of each individual piece is less than the absolute value of the guys without individual absolute values inside. Okay, now look, these two guys, when I distribute that, will cancel. And we're just left with the 4n times x minus the 4n times x, like I said, cancel. We're left with 4 to the n delta sub m over delta sub m, and that's equal to 4n. Okay. Now, another thing we need to observe is that the gamma of m is absolute value, which equals to the absolute value of the 4, this will be m times x plus delta sub m minus phi of 4m times x all over the delta sub m. Now, what I want to tell you is that we had chosen that delta sub m so that the distance between this guy and this guy doesn't contain an energy. When I look back at that graph of phi, now that's beautiful. Continue on just a little bit. Okay, look, as long as there isn't an integer between these numbers, so we're looking at two numbers where there's no integer between them, it's like in one of these gaps between these integers. And you can see that the phi of them would be on this, both phi of each one of those points will be on the same, I'll say, line segment, like this one or this one. And so the difference between them inside absolute values has got to be less than or equal to 1/2. That's what we get. Because here, when you multiply this out, this is going to be less, plus or minus 1/2. So they're just half unit off from each other within that region between integers. Over this delta sub m is 1/2 of 4 to the minus m, and then that's just going to be equal to 4 to the m. Oops, I think I'm writing a little bit too far. So this is going to be equal to 4 to the m. And I shouldn't have said less than or equal to. It's equal, because they're exactly half the unit off. That's what these are. These points are exactly half the unit off. Okay. So, that absolute value of f of x plus delta sub m minus f of x over delta sub m is going to be equal to, okay, this is the sum as n runs from 0 to infinity. 3/4 raised to n. Phi, I don't have that one here. Excuse me. Equal to the absolute value of the sum as n runs from 0 to infinity of 3/4 to the n. Phi of this will be 4n times x plus delta sub m, and that's that part, minus the sum as n runs from 0 to infinity, 3/4 to the n, phi of 4 times n, 4 raised to n times x, all over the delta sub m. These are two convergent series. We can combine them. Get the sum as n runs from 0 to infinity of 3/4 raised to the n, phi of 4 to the n times x minus delta sub m, minus minus phi of 4 to the n times x. Okay. It's not minus here, it's plus. Let's see right now. All over, and I'm going to pull the delta sub m from inside the sum because it's a constant with respect to that. Let me end my absolute values here. And then finally I'll say, hey, that's the same thing as the absolute value of the sum as n runs from 0 to infinity of 3/4 raised to the n. And this is nothing more than what we defined to be that gamma of n. Gamma sub n. Okay, that's what I got. And I'm going to write down one more thing here. This is equal to, now look, what we said was this gamma sub n was 0 when n is bigger than m. And so this really becomes a sum just from n running from 0 to whatever that fixed n was, of 3/4 to the n times gamma sub n. Okay? Okay, now that's equal to, so I'll break it up, that sum, into two parts. So the last term, which is going to be 3/4, is just going to be when n is equal to m. Gamma sub m, and then it's going to be plus the sum as n runs from 0 to m minus 1, of 3/4 to the n, gamma to the n, Now, what I'm going to do next is I'm going to be using using that the absolute value of A minus the absolute value of B is less than or equal to A plus B. So this is my A, this is my B. So I'm using this. So what I'm going to have is this part is going to be greater than or equal to. Okay. So this part is greater than or equal to, so I'm going to write down this part. So it's 3/4 to the m, gamma sub m, minus the absolute value of the sum as n runs from 0 to m minus 1, of 3/4 to the n, gamma sub n. This part I know what it is. I'm going to have less than or equal to, not because what I'm going to do here. This part is 3/4 to the m, and then the absolute value of gamma sub m, we found that to be I think 4 to the m. Yeah. Okay. This part, I'm going to say it minus the sum. So I'm going to bring the absolute values inside, and when I do,
this quantity becomes bigger. And so I'm taking away something bigger, so overall, this becomes smaller. This line becomes smaller. And so this is n runs from 0 to n minus 1, 3/4 to the n times the absolute value of gamma sub n. Okay. Now, we know we got something bigger than this, I think. Okay. So this is 3 to the m. That's what I got here for this part. And then minus, okay, this is going to be the sum as n runs from 0 to m minus 1 of 3/4 to the n. And then the gamma sub n, we're going to replace it with 4 raised to the n. Okay? Now, the 4 to the n is bigger, so we're taking away something bigger, so that got smaller. That's what we have.
Okay.
Okay. This is going to be equal to 3 to the m minus the sum as n runs from 0 to m minus 1. And then from the previous sums, the 4 to the n's are going to cancel out, and we just have a 3 to the n. And this is a finite geometric series, and we had a formula for that. We've used it. So it's 3 to the m minus, and the quantity is going to be 1 minus 3 to 1 higher number than here. That's 3 to the m. Over, it was 1 minus 3. And so that's equal to 3 to the m minus, well, this will be minus 2, so let's make this plus. 1 minus 3 to the m over 2. Getting a common denominator, we have 2 times 3 to the m plus 1 minus 3 to the m all over 2. The 2 3 to the m minus 1 3 to the m's yield a 3 to the m plus 1 over 2, which our text proves says it's 1/2 3 to the m plus 1. Okay, that's great. That's what we got. Okay. What this quantity was something related to the m acting on x plus delta sub m minus f of x all over delta sub m. So that quantity that I just called out inside absolute values is bigger than this. So we'll just show it. Now, although our definition for a derivative is equal to the limit as t goes to x of f of t minus f of x all over t minus x. Okay, that's what it is. This is equivalent to the limit as h goes to 0 of f of x plus h minus f of x all over h. And that's a definition that a lot of calculus books will use. That's equivalent. And that's going to be equivalent
to, well, essentially the same. The limit is delta sub m goes to 0 of f of x plus delta sub m minus f of x all over delta sub m. Okay? This is the same. I'm just substituting in delta sub m for h. Okay? Now, if you pause for a second and think about as m goes to infinity, and what I want you to think about is the delta sub m. Now that was that plus or minus 1/2 times 4 to the minus m, and so it's it's 1 over 4 to the m. So as m gets really, really big, this goes to 0, so this goes to 0. Okay? That's what happens. Okay. So since the absolute value of f of x plus delta sub m minus f of x all over delta sub m is going to be greater than or equal to what we had just a second ago, that 1/2 3 to the m plus 1. Then, you know, as delta sub m goes to 0, as m goes to 0, okay, this guy goes to what we hope to be the derivative, but this guy, as m goes to 0, is going to go towards infinity. That says the limit as delta sub m goes to 0 of the f of x plus delta sub m minus f of x all over delta sub m, that guy does not exist. So, since that means that the derivative does not exist at x, but x was arbitrary, so f of x is nowhere differentiable. And that's the proof. Excellent. Okay, I'm going to go over some definitions, examples. And this is kind of a subtopic in our exploration of sequence of functions. Okay? Well, terms varying from being somewhat, from it being uniformly converted or not. So here, let f sub n be a sequence of functions defined on a set E. Okay? We say the sequence f sub n runs from 1 to infinity, of course, is pointwise bounded on E if the sequence f sub n of x is bounded for each x in E. So the bound for this sequence of numbers is going to depend on x. So it's like the absolute value of f sub n of x is going to be less than or equal to some big M subscript x, because that M depends on x. And another way of saying that
what the book says, which is, in other words, f sub n is pointwise bounded on E if there exists a finite value function called phi such that, phi defined, I should say, on E such that the norm of f sub n of x is going to be less than or equal, or less than phi of x less than or equal to good as well. For all x in E where n is equal to 1, 2, 3, for all of them. Okay, so that's the definition of pointwise. Well, kind of like when we had pointwise convergence, and then we had uniform convergence, we have this pointwise boundedness, and we're going to have this uniform boundedness. And so the pointwise has to do for each individual x, we get a bound. For the uniform, it's going to be that there's one bound that works for all x. You know, I want to stress that a little bit for the convergence pointwise. There was an n that worked for each x for the pointwise convergence. For the uniform convergence, there was one n that worked for all x's. Okay. So here's the definition. Let f sub n be a sequence of functions defined on a set E. We say f sub n is uniformly bounded on E if there exists a number m such that f sub n of x is going to be less than m. Okay? And that's for all x element of E and for all n equal 1, 2, 3, so one number works for them all. Now, as a fact, before we do some examples, it says if f sub n
is uniformly bounded on E. Then f sub n is pointwise bounded. Okay. Well, here's the proof. It's very, very simple. We let f sub n be uniformly bounded on that means then there exists an m such that absolute value of f sub n of x will be less than this m. Okay, and that's for all x element of E and for all n that are natural numbers. So that means for each x element of E, we have, if you fix it, f n sub x will be less than m, and that tells us, and that's for all the n's. I ran out of space, I'm sorry. And that's true for all the n's. 1, 2, 3. Okay? Thus, f sub n's are pointwise bounded. Okay? As an example, if we consider that f sub n of x equaling to x squared minus 1 over n, then for each x n r, so I'm defining it on r, f sub n of x inside absolute values will be less than or equal to x squared. That's my function b of x. You know, in the proof that the uniform boundedness implies pointwise boundedness, the phi for the pointwise root of that constant. Okay. So we have this. So this collection of f sub n's are pointwise bounded. However, they're not uniformly bounded. And the reason it's not uniformly bounded is I'll write a little bit more details about that. Is that we'll say because for every m that's bigger than 0, so no matter what constant we pick, there exists x
and I'll say, hey, just take x equal to n plus 3, that's in R, and at n, just something like 100, such that the absolute value of f sub n sub x, that's n plus 3, is going to be greater than or equal to the m. And I'll let you go through the details of that. That's going to be enough for today, but before I conclude, I want to say I'm really grateful to be looking at this type of distinction with the boundedness, pointwise or uniform, because it's very similar to that of the distinction between convergence pointwise and convergence uniformly. And so what I did here translates into the convergence part as well. Okay? So if you didn't get it before for the convergence, this gives you another chance to get it. If I didn't explain it as well as I could have before, it gives me another chance to explain it. So that's what I'm grateful for. Thank you very much.